Uh, Hello, welcome to the channel. Today we're going to talk about momentum, and specifically we're going to talk about momentum within the context of rocket motion, And basically, rocket motion is, a rocket, where there's a mass m, and there's a mass dm, which is ejected, by the process of propulsion, and whatever, there's an explosion and some chemical reaction goes on, the reactants sort of like go on in the opposite direction, which gives a boost to the rocket due to conservation of momentum. But we're going to see how in this video, and specifically we're going to derive the fundamental equation of rocket motion from first principles. Okay, so what is momentum? Number one. Let's look at the second law of motion. Okay, in classical mechanics, it's m multiplied by a, where a is a vector, force is a vector. Okay, this is the familiar form. You might have seen it very often, but there's another way of writing it. We know that F is also equal. Let's rewrite A in this way as the derivative of velocity with respect to time. Velocity is also a vector. This is another way of writing it, which is equivalent, because notice that this is just A, the form. Then I'm going to sort of like say that since this is a function, and I'm sort of like deriving a function multiplied by a constant, I can sort of like take the constant and put it inside the derivative, which I'm going to do. And so in doing so, I'm going to get d dt times mv, where m is a constant and v is a vector or function. And now we have a new expression where this term sort of like appears, and this term is called momentum. Okay, this quantity is called momentum. mv is the momentum, mass multiplied by velocity. This is a quantity which is more fundamental in some ways to mass and velocity individually. Of course, mass is invariant, but velocity is very relative. Momentum, by virtue of being a function of velocity, is also relative. But in a system where these things are decomposed and the velocity might vary in terms of like different objects, sort of like in an explosion or in the context of propulsion, which is the right context for looking at rocket motion, momentum is going to be really fundamental and really useful. And another way to write this is we're going to write it as P, and the equation now takes the form of F is equal to dP dt, which is the derivative of momentum. Force is equal to the derivative of momentum being a vector quantity. Now, I just rewrote the second law. These two formulations are equivalent. So nothing new here fundamentally, mathematically speaking, but this is just a more powerful way in the context of physics problems to find the results, where you have dynamical quantities that are changing and a body which has multiple parts. Sort of like in the context specifically, very often you're going to see explosions or ejections and propulsion. Okay, anyway, so this is a way of defining momentum, and another way of defining momentum is in this way, which is very standard. The vector momentum is m times the vector velocity. Okay, now let's look at rocket motion very quickly. So basically you have a rocket, it goes like this, and maybe at time t, the mass was m plus dm, sort of like the body of the rocket plus the fuel inside it. And now the fuel has sort of like chemically reacted with something, and there's an explosion, and all of a sudden you have all of this mass coming out of the rocket in the opposite direction, And let's say it's going at like speed u with respect to the rocket, but let's say we consider that initially the velocity was v, and at time t plus delta t, the velocity is now v, the velocity is now v plus delta v. Okay, and now you have the velocity of v plus delta v after ejection. You have a mass of m, you know, but in the opposite direction, since the velocity of the ejection was u with respect to the rocket, now you have to sort of like do the theorem of additional velocity, because in this frame of reference, we're not at rest with respect to the rocket anymore. The rocket now has a velocity with respect to us. And so if it has a velocity with respect to us, you have to apply the Galilean theorem of additional velocities. So as a consequence, you're going to write the velocity of the ejected fuel as v plus delta v plus u. Okay, and so these are sort of like initial conditions and final conditions. And now we're going to think about momentum for both conditions, initial conditions and final conditions. Initially, at p of t, the momentum is given by the total mass, which is m plus dm times v. Okay, so the velocity of the thing is v, and at some time t plus t delta t plus delta t, the momentum is now m times v plus delta v plus now this is going at this velocity, which is v plus delta v plus u. So this momentum, and by the way, what I'm really doing is I'm multiplying the mass value times the velocity value. So the entire thing, you know, was the full mass of the ship plus the fuel times the initial velocity. Now in this case, we're going to have this part of the body of the rocket, which is has a mass m, going at v plus delta v. So it's going to be the mass times the velocity, and this part of the thing is also is part of the total momentum. We're looking at the entire system, so I have to also look at this. And on this side we have dm as a mass, and as a velocity we're going to have v plus delta v plus u. We have v plus delta v plus u. Okay, so now we're going to look at the difference in momentum, you know, because this equation sort of like relates the difference in momentum, you know, the derivative of momentum with respect to time. And, you know, with respect to time, there's a difference of delta t, you know, so what is the difference of momentum? What is the derivative of the momentum with respect to this time difference? So what we're going to do is we're going to subtract these two values simply, you know, so, you know, delta p, I might write, is equal to p final minus p initial. Okay, so this is sort of like how it goes very symbolically, and more specifically, we're going to subtract this value from this value, which is the final value from the initial value, and this multiplies what's inside the bracket, so we have mv, and we also have mv in the first part of the equation times m plus dm. So we have mv, you know, is going to cross out mv, you know, and dmv is also going to cross out dmv. So we're going to be left with m. So this whole entire equation is crossed out, and what the terms we're being left with is m times delta v plus dm plus delta v times u. So let's write this. Now we have delta p is equal to m delta v. Let's write it very neatly. We have delta p is equal to m times delta v plus we're going to have dm times v delta v plus u, dm plus delta v plus u in parentheses, and this is delta P. Okay, now we've made some progress, okay? We almost had this equation back, but we noticed that, okay, we've taken a derivative, so we're not talking about a difference, we're talking about actually a derivative, an infinitesimal rate of change. So we have to take the limit. So very interestingly, we see that it's divided by dt, so that's what we're going to do. We're going to divide it by delta t. We divide it by delta t, you know, or, I mean, we can just immediately take the derivative. We're going to take the derivative of p, you know, with respect to time. And on this, in this case, I mean, this is equivalent to dividing it by delta t, and I'm going to have the delta t on this side, just because it just sort of makes sense in terms of the derivation. And what it really means to have the derivative is to take the limit as t approaches 0, because we have dt, which is an infinitesimal fraction of t. So we're going to take the limit as t approaches 0 of this whole entire expression, you know. So this goes to dt, you know, it goes to dt. Now, this was a velocity difference, but as t approaches 0, it goes to 0, or it goes to dv, to be more specific. You know, it goes to something very small, very infinitesimal. And so does the delta t in here. And delta v in here, actually, because it's not, we're not taking this derivative on this side, we're just taking a derivative with respect to, I mean, there's only one dt multiplying this whole entire expression. This sort of like comes across as a function, and so delta v as t approaches 0 is just going to go to 0, because in 0 time there's no velocity increase. So this is just going to go to 0. So there's going to be u inside the bracket, you know. You might rewrite this in a specific form, you know, u dm divided by dt. Okay, so now you sort of like have the whole entire expression in its final form, in the way we look at it in rocket motion. But we just want to look at the meaning of this and add one more modification with respect to the meaning. What's going on here? We notice that this body of mass, which was m plus dm initially, you know, loses mass. So the derivative of m, you know, which is the change in mass of the whole entire system, you know, which is a mass called dm, which is an infinitesimal value of mass, you know. We're looking at the problem very abstractly, you know. This might be a real quantity, but it's just a change in mass, you know, very abstractly. This change in mass is going to be a subtraction from the initial quantity of mass. So therefore, the derivative, you know, which is just a rate of change in mass, is a negative rate of change. You know, it's a negative rate of change. And so this is the final expression. The derivative of momentum is equal to m times the derivative of velocity minus u times the derivative of mass. Okay, and this is the way to look at rocket motion. And this equation is going to be very useful in solving problems for rocket motion. So thanks for watching the video. I hope you really enjoy it. We're going to do a problem next time using these fundamental concepts, and I hope the thing is very clear. Let's look a little bit deeper at the meaning of this. We have the mass of the rocket, you know, and it's changing velocity because it's increasing. You know, propulsion implies that this dejection really changes the velocity of the ship. Okay, so it's accelerating. So we have an acceleration in here. Okay, and now we have the velocity of the thing that's being ejected with a change in mass. So there's a change in mass related to the velocity of the thing being ejected, and there's a change in the velocity of the ship as a consequence of this being ejected, which is equal to a total force, you know. And that's really it, which is, you know, maybe the force of the explosion related to the combustion inside the ship. Okay, so thank you for watching the video. You know, if you enjoy this type of content, please like and subscribe, and I'll see you in the next video.